My name is Anna, as Ellen already mentioned. So today my talk is about the small possibilities that Go isn't memory safe anymore. So it's mostly theoretical, but nonetheless it's important, I think, to be aware that you can get also Go to be memory unsafe. If you want to take something out of the talk, I think it's just this awareness that just because the language is memory safe, there are possibilities to break it. And the talk, I will shortly introduce it. And everything I will tell you here is not confidential, so most of the resources are either published or also are written down in blog posts from the Go's beginning area, which is nearly 10 years ago, but it's still valid. So let's dig into it. To start with, memory safety, to get all on the same stage. In general, it basically means that your programming language can help to protect from software bugs and also security vulnerabilities like buffer overflows, which happens due to memory access. Why do we have these kind of bugs? These are mostly due to memory unsafe languages like C, C++, which allow arbitrary pointer arithmetic, that is, do crazy computations with pointers, and also allow to directly access pointers, and therefore memory access. And also for arrays, you have no bound checks. In contrast, we have more modern languages, which are usually called memory safe, like Rust, Go, C#, Swift, Python, and Java, which implements protection mechanism against these vulnerabilities, for example, with out-of-bound reads and writes and avoiding dangling pointers. Why do we need out-of-bound reads and protection against dangling pointers? On the left, I did introduce you to Go, and one of the mascots of Go is the gopher, which you see on the left. And basically, your memory is like a long list. And if you have an array, which is on this call, in this case, simply the list of talks of this year's BSides, you actually want to access only the valid elements of your list. So if your gopher asks for the 13th talk, spoiler, we only have 12 talks. And actually, this is in theory off by one error because talk 12 on your or in the corresponding Go program will already be an out-of-bound. Should give your message or something like you're doing something which you're not supposed to do. That's what a memory safe language would do. A memory unsafe will simply ignore this information and go to the next or to the corresponding memory element. In this case, it would be the next confidential information that there may be, I don't know, a speaker dinner afterwards for all speakers. And of course, that's confidential information. And if you imagine your real program, that's an issue. Yes. And you could also argue that if you use a language which doesn't have these checks, that it's the developer's responsibility. But actually, that's bugs. So, I mean, it could happen that you implement a bug, and we all know we are human, bugs happen. So, having memory safety is a nice thing to have. Now, covering shortly pointers. If you're delayed or tomorrow, the BSides organization team is very enthusiastic and already deleted all talks of this year's and updated the welcome words and closing remarks to next year. And if now our curious scoffers want to get the first, second, or whatever talk for next year, he should get the information that there are no talks because the talks of this year were deleted. But if you have no protection against it, you will get simply the first word. Because you can fetch memory where the program actually said it's done and may be used for something else, but maybe not be used for something else yet. These kind of vulnerabilities are also called, for example, use after free vulnerability. And I marked the pointer as dashed because it's a dangling pointer. Of course, these examples are simplified, but should give you an impression why it's important to have memory safety. Shortly, for those of you who are not familiar with Go, Go is a statically typed and compiled programming language with memory safety and, for example, garbage collection and CSP style concurrency. And many more features, but I think that's enough to get an impression of Go. And for example, the memory safety for this Go also checks for bounds, for slices and arrays. Slices are basically arrays in Go. If you don't know them, that's enough to know. They also have restrictions to this type system, and you can't have you don't have dangling pointers. Of course, so what does that mean in practice? That Go has bound checks. That basically mean that if you want to access an element which is out of bound because it's, for example, the element is too high, you get a runtime error. How does that look like? If you run your Go program, you can get a panic with some runtime error and a message like index out of range. Now, I hope that you have an understanding why memory safety is great and that Go is actually doing pretty good in it. But what can we do, or not what can we do, but what is possible to break the memory safety or to play against the rules? So basically, we have 3 ways to circumvent the memory safety measurements implemented in Go, or at least 3 ways I am aware of. The first is the UNSAFE API. That's basically an API which allows you to avoid these type safety measurements implemented in Go and also directly access the memory addresses. Valid cases for this are like optimization, hardware access, and also access to external libraries, for example, C libraries. Then there's concurrency due to data races, and that's actually a more subtle and indirect way to break it. And of course, if you link C or C++ programs, those programs are not have the memory safety measures, and I think they have to be a bit separated because C or C++, you don't go. But now let's look shortly into the problem of a concurrency problem, why we can get memory unsafe there. I tried to simplify it because I think in this talk you should only get the idea with you that it can be a problem. If you are interested in the concrete Go code, you could get later links where you can really dig deep into this. And I wanted to give you the idea of it. The problem is that slices interface values and strings are multi-word values. Meaning that in the case, for example, for the interface, 2 instructions are required to update the values. Because an interface in Go is basically represented as once the type, which points to the type, and the data, which also may be a point. So in Go, we have kind of 2.5 ways to circumvent the memory safety in Go. The first is the UNSAFE API. And this API basically allows you to avoid type safety measures implemented in Go and also to directly access memory addresses. And there are also a lot of valid cases to use this API, like optimization or hardware access. And the other way is concurrency or data races, which can also cause memory and safety issues. And the halfway, which is obvious, is linked C and C++ programs, because if you link C or C++ programs which are not memory safe, they of course don't have the measures. Now, shortly look into why concurrency is a problem. So, Go has multi-word values, which are namely slices, which are basically erased in Go, interface values, and strings. While the later, strings, are immutable, and thus it's only possible to read memory and not write to it, for slices and interfaces, we can also manage to write into the memory. Why this happens? Basically, because looking at the interface example, to update an interface value, we require 2 instructions instead of 1. So if we don't synchronize our access to the interface value and get a data race, it may happen that one routine updates one part of the interface value and the other update the other part, having kind of something old and something new. And this we can use to get memory and safety behavior. Now, to get you an idea how this exploit works without digging too deep into the code, I've created these images. Let's start. Because we want to exploit that an interface value requires 2 instructions, we build up an interface. Our interface in this example is xer, which simply adds the method x. We define 2 structs. The first is called safe, and f is a pointer to int, which implements the method x, and thus implicitly implements the xer interface. In Go, you don't have to explicitly define that you implement an interface. As soon as your struct has the methods of the implements, it implements this interface. And the struct unsafe, which have a func or expects a func for f instead of a pointer to int. Then for unsafe, our method x does a bit more and checks if f is not null, which is the null in Go, and if that's the case, it calls this function. Now, if we mix that up together, we want to have one variable confused of this interface, and of course the good and bad variables. The good, first we assign or create a struct value where we pass for f the address of a function win. I omitted the function for simplicity. And for bad, we simply create an empty struct of unsafe. So we don't pass a value for f, so it's nil. And then we assign to confused good. Until now, everything is looking good, but you can imagine if we start to put concurrency on it and come to data arrays, we can come into a situation where confused is part good and part bad. And that's the exploit, basically, or how it could like. We start, for example, to Go routines, which set confused to bad and afterwards to good. And then we have one for loop which runs forever, like the other two in the Go routines, which called the function x on confused. If you remember, for good, nothing happens. It's simply. And for bad, it checks if f is set. But for bad, we didn't set any to f, so it's null, so it wouldn't execute unless f points already to the address of the win function, which is parsed as the f in good. If that happens, the program stops because we simply put on win the function an OS exit. So, summarize, that's how you can get from that's the basic idea how you can exploit data races to screw up your memory safety. Of course, going or have flags such that you can detect the data races. You simply put the flag -race to it. That curses that you get information that a data race was detected and it still executes, so your exploit will still be applicable. If you want to avoid that and force a stop of the program, you have to pass GO-GEIGER equal hold on arrow equal 1. Now, after this short glimpse, dig deeper into it or see sources on this actually. There are two introduction level blog posts about this issue. The first is from Russ Cox of the Races, where he described how slices and interfaces can screw up your memory safety, and he also argued that it's not a security issue because normally you don't execute code you don't trust in your environment. And Stalker, and then there's the other blog post by Stalker, which is called Go Long Data Races to Break Memory Safety, which is also, I think, nice to read. And my examples, or the examples I tried to break you down in these slides before, are also orientated on his blog post. In case you still think, well, that's boring, I really, really want to dig deeper into it. There's a nice write-up of a Capture the Flag challenge of the Gomian brother, where they also make actual useful vulnerability or to break into the system with this memory safety issues. Now, having said that, I surely want to cover the Unsafe API. The Unsafe API is an escape hatch if you really need to go down to your memory and play around with the addresses. As mentioned before, there are legitimate use cases, and basically the API allows you arbitrary typecast and pointer arithmetic. And as you can think, that also circumvent the memory safety measures. If you ask, can we make exploit with this? Of course you can, or we can. There is one nice blog series from a student of mine who tried to make some exploits with unsafe pointers. I think it's in total 4 parts. If you want to see more on this, also with examples, you're good to go there. And in case if you wonder if that's a problem in the world or in the wild, we also have published a paper recently about this. So if you want to dig more into this area, there are probably good pointers. Now, to score the points, GO-GEIGER is the answer. But actually, what does GO-GEIGER do? So what I mentioned, the study I mentioned before, is kind of theoretically, and it doesn't apply to your code base. And probably you're interested, or perhaps you are now interested, how much unsafe is used within your code. In that case, you simply can run GO-GEIGER, which is similar to the Rust Geiger the Rust Geiger tool, which simply lists you all unsafe usages within your code, but also in your dependencies. Now, to sum up the talk, which was kind of interrupted, and now a bit faster. Go is memory safe, and the runtime really checks for you and does a great job in this respect. You can break it a bit if you play around with the unsafe API, or if you get data races with concurrency and get the program into different states, as I show you with the interface example, and that really would work in practice. And if you're interested in whether your projects actually use unsafe or the unsafe API, you can audit your code base with GO-GEIGER. And that's it. Thank you, and also sorry for the interruptions.